In this video, we're going to be talking about logistic models with differential equations. Let's start by talking about what a logistic model is. So we've talked about exponential models where a population grows exponentially, but not every population can grow exponentially. Imagine in an environment, as the population is growing, at some point, food, water, money, resources start to run out and the growth levels off and approaches what we're going to call the carrying capacity. So I have a little graph right here. You can see in the short run, it looks like we're growing exponentially, but at some point, the population growth levels off and approaches this carrying capacity, which we call L in calculus. So this is our logistic model. And then it says over here, when the growth rate of a population is proportional to the current value and how far the current value is from the carrying capacity, it is called logistic growth. So if the current value of the population is Y and our carrying capacity is L, that means that how far the current value is from the carrying capacity is L minus Y. So we have this differential equation that we're going to be using. We also have our graph in a slope field. So you can see that no matter what the initial value is, our population will at some point reach that carrying capacity. And so we say that the limit as t goes to infinity, t being time, of y of t, you approach L. I also want you to notice that I could have an initial value that's above the carrying capacity. So for example, let's say we have, I don't know, a pack of wolves and we have too many wolves for the environment. Some of those wolves are going to die off and you're still going to reach that carrying capacity. So we could have an initial value above the carrying capacity. So we have our differential equation, dy dt equals ky times L minus y. And notice that this differential equation is separable. So we could separate it, we could solve for y, all those things. It is a lot of work, so we're not going to show it in this video. But eventually you get this y equation. Again, L is the carrying capacity. And then you have k, a constant, and c, a constant. So these are the two equations that we're going to be using in all of our logistic growth examples. Another thing to point out is you always have, when you have a point of inflection in your logistic growth, it always occurs at L over 2. And so that's going to be our carrying capacity divided by 2. And at L over 2, at this point of inflection, notice that this is where your population is growing the fastest. So we might get some questions like that when we do our examples. So let's do some examples. Starting with this one, it says the growth rate of a population P of bears in a newly established wildlife preserve is modeled by this differential equation. Notice that this looks like our dy dt equals ky, let's use a different color, equals ky times L minus y. And they're saying that t is measured in years. Letter A, what is the carrying capacity for bears at the wildlife preserve? Well, if we know our differential equation, we know that L is 100. So we're going to say 100 bears. Letter B, what is the bear population when the population is growing the fastest? We know that the population is going to grow the fastest at the carrying capacity divided by 2. So in this context, it's going to be 100 divided by 2, which is 50 bears. Part C, what is the rate of change of the population when it is growing the fastest? So for this one, we want the rate of change, so that's going to be dp dt. When the population is growing the fastest, we know that's when the population is 50. So we're going to plug 50 into our dp dt. Times 100 minus 50. And notice this is 0.08 times 50 squared. And I'm just going to tell you that that equals 20 bears per year. So this is our first example. Example 2, this is a calculator question. It says the population of Alaska from 1900 to 2000 can be modeled by the following logistic equation. So they gave us this logistic equation, and I want you to notice that it looks like the one I showed in that box on the previous page. So because we're using this equation, we can also use, and we're going to have dp dt again. So we may be using one or both of these two equations. So it says where P is the population and T is years after 1900. So that's going to be important, with T equal to 0 corresponding to 1900. Letter A, what is the predicted population of Alaska in 2020? So I want the predicted population of Alaska in 2020. T is our number of years after 2000. I'm sorry, after 1900. So that means T equals 120. So if I want the population, I want P of 120. So since this is a calculator question, let's have the calculator do all of the work. I want you to notice that I've already plugged in our population equation into Y1. So I can go back to my regular screen, and it might be different depending on your calculator, but I can say alpha trace Y1, and I want Y1 of 120. And that gives me this answer. So on my page, I'm going to round. So let's write it out first. It's 781,217.6016. And they're asking what is the population going to be? So I'm going to round to the nearest whole number. So we get 781,218 people. Okay, part B. How fast was the population of Alaska changing in 1920? So notice they're asking about a rate of change. So they're asking how fast was the population changing? So I want dp dt, and they're asking what in 1920, so that's when t equals 20. So I want to evaluate the derivative at t equals 20. So I'm going to go back to my calculator. So on my calculator, I can say math, and then derivative is my 8th option. In my calculator, it's in terms of x, and I want to take the derivative of my y1 at x equals 20. And we get 1678 people per year. Then it also says in part B in 1940 and 1999. So we're going to do the same thing. We're going to evaluate at 1940 t equals 40. And then in 1999, right, 1999, t equals 99. So I'm going to go back to my calculator, and I'm going to plug in 40, and I'm going to plug in 99. So I get those two values. So going back to my work, we get 4127 people per year, and we get 9741 people per year. So that is part B. Part C, when was Alaska growing the fastest, and what was the population then? Well, we know that the population is going to grow the fastest at the carrying capacity divided by 2. So I'm going to look back at my equation. Notice that this numerator is your carrying capacity. So I'm going to take 895598 and I'm going to divide that by 2. And that gives me 447799. So I'm going to say the population is growing the fastest when P of t equals 447799. So we answered what was the population then. So the population was 447799. And then they want to know the time as well. So to find the time, I'm going to do this using the calculator again. So going back to the calculator, I want to know where P of t equals 447799. So I'm going to make y of 2 equal 447799. And I'm going to graph this. Let's choose a window. So this is the window that I'm going to choose. Let's see if it looks okay. Okay. And then I'm going to say second calc, and I want to know where those two graphs intersect. So they say first curve, second curve. I know they only intersect in one space on this graph, so I don't have to be super accurate with my prediction. So I'm just going to say right there. And they intersect when x equals 82.765. So that's going to be my t value, my time when the population is growing the fastest. So I'm going to say t equals and if t is in years after 1900, this is going to be 1982. Oops. And if we're 0.765, we're about 3/4 through the year. So we can say we're September of 1982. So I'm going to say the population is growing the fastest when the population is 447799. Which is in September of 1982. That's part C. We have a part D. It says, what information does the equation tell us about the population of Alaska in the long run? Well, in the long run, we can take the limit as t goes to infinity of P of t. And we know we're going to approach the carrying capacity, which we said is this 895598. So we can say the population will approach 895598 people. And that is our second example. Here's our third example. It says given dPdt equals, and then we have this over on the right side of the equation. Now this doesn't flat out look like our dy dt equals ky times L minus y, but we can manipulate it. What if I factor out, I want this to be the second term to be my y. So I'm going to factor out a 0.002 p. And when I do that, 0.2 divided by 0.002, that's going to be 100. And notice now we're in the form ky times L minus y. So letter A, find the carrying capacity. That's going to be 100. I'm going to say carrying capacity. Letter B, what is the population when the population is growing the fastest? The population is growing the fastest. That's going to be the carrying capacity divided by 2. So that's going to be 50. So the population is 50 when it's growing the fastest. Letter C, what is the rate of change at a time when the population is growing the fastest? So we want dp dt when the population is growing the fastest. So at p equals 50. So we're going to plug in 50, 0.002 times 50 times 100 minus 50. And when you multiply all this out, we get 5. And it's going to be 5. They don't give us much information about the population, but we can say people if we're talking about people per whatever our unit of time is. So I wanted to do this example to show you they might not give you exactly ky times L minus y, but you will be able to manipulate it so that you can answer the questions. So this was number 3. We have one more. This one says the rate at which the flu spreads through a community is modeled by this logistic differential equation, where t is measured in days and t is greater than or equal to 0. If p of 0 equals 50, solve for p as a function of t. So for this one, we are going to be using our y equation. So let's start with our generic y equation. And let's put it in our context. So instead of y, we are using p. So we're going to say p of t equals the same right side of the equation. Okay, and we can see that if this is ky times L minus y, we can see that our L, our carrying capacity, is 3,000, and our K is 0.001. So let's plug those in. Okay, let's make this a little bit simpler. Negative 3,000 times 0.001 is going to be negative 3. So now that we have that, we still don't have C. So we're going to use the P of 0 equals 50. So I'm going to say 50 equals, and I'm going to plug 0 in for T. So this is 1 plus CE to the 0. And let's solve for C. So this is going to be 50 over 3,000 equals 1 over 1 plus C. So let's flip these. I get 3,000 divided by 50 equals 1 plus C over 1. 3,000 divided by 50 is going to be 60. Let's write that better. So C equals 59. So let's write our final equation. We're going to say P of t equals 3,000 over 1 plus 59e to the negative 3t. And that is our first answer. Letter B, use your solution in part A to find the size of the population when t equals 2 days. So for part B, we're going to plug in 2. So I get 3,000 over 1 plus 59 e to the negative 6 when I plug in that 2. And I'm just going to tell you, when we plug that into a calculator, we get about 2,617 people. Letter C, use your solution in part A to find the number of days that have passed when the flu is spreading the fastest. So the flue is spreading the fastest at the carrying capacity divided by 2. If L is 3,000, that's our carrying capacity. So 3,000 divided by 2 is 1,500. So I'm going to set up my equation when the population is 1,500. I want to solve for T. Okay, so I'm going to multiply by this denominator on both sides, and I'm going to divide by 1,500. So I get 1 plus 59 e to the negative 3t. 3,000 divided by 1,500 is 2. And then I'm going to subtract 1 on both sides, divide by 59 on both sides, natural log both sides of your equation, and divide by negative 3 on both sides. And when we plug this in to our calculator, we get about 1.359 days. Okay, so those are a few examples of using logistic models with differential equations. Thank you for watching.